All right. So let's begin. So today the class will entirely focus on minimum spanning trees. And minimum spanning trees are a great, we'll go over some of the applications, we'll talk about the Curtin cycle, review the Curtin cycle properties that we started covering last time. We will go over Kruskal's and Prim's algorithm, and hopefully we'll have time to analyze the running times, otherwise I will throw up the next class. But minimum spanning trees are also a very good tool to understand graphs. And we will do examples of proofs as to properties of minimum spanning trees. And they also are an excellent example of what greedy algorithms look like. Both of these algorithms are greedy. Okay? All right, so recall what was the MST problem. What you're given is an undirected connected graph. And you have weights on the edges. Okay, with weights on the edges. Again, that notation indicates that this is the set of all positive integers. And your goal is to determine a spanning tree of G of minimum weight. Okay? Very clearly stated problem, well defined. Some applications of this. So one example is in chip design, in VLSI layout, for example. You might have a chip where there are a lot of pins that are supposed to get the same value, and you want to connect all these pins together with wires, but wiring is always a big challenge. You want to use the minimum amount of wire, both to reduce the amount of delays as well as reduce the amount of energy used. So and there is of course an underlying sort of grid structure which allows where the wiring can go from. So maybe you can make these, or you want to be able to connect these, and there might be a way to maybe draw a wire from here to here, draw a wire from here to here, draw a wire from here to here, so on. So the minimum spanning tree will try to find out the wiring that will connect all of these pins with minimum amount of wire. Okay. A similar example occurs in problem of multicast communication in a network. In a multicast scenario where there is like maybe some kind of streaming going on between one sender and a bunch of receivers, or there is an all-to-all communication going on, and you have an underlying network, you have a bunch of players that are participating in this multicast, or a bunch of nodes that are participating in this multicast. You want to find the minimum bandwidth. Actually, in this case, it's not minimum bandwidth, minimum latency links that will connect all of them, maybe here, so that the total amount, maybe there is a cost associated with each of these edges, the total amount of cost you incur. More often, minimum spanning trees occur as sort of sub-problems within other problems. And the Kleinberg-Tardas book has a number of different examples where minimum spanning trees come up again and again, so I urge you to look at those. Okay. But as I mentioned, in addition to their applications directly, so this problem has been studied for about 100 years. So in addition to where this problem appears, it's also an excellent tool for understanding greedy algorithms, for understanding graphs, for understanding proofs about graphs. So please pay close attention to this. It also will lead us to interesting questions in data structures, which we'll talk about towards the end of the class. Okay, so as I've mentioned many times, whenever you're faced with this problem of, okay, find me the best possible solution, before trying to come up with an algorithm, we have to try to understand what this solution looks like. Okay? And there were a couple of observations we made last time, and those observations were what referred to as the cut property. And the cut property says that let S complement, okay, S complement means all the vertices not in S, be a cut in G, then and T, V, and MST of G, then T contains a minimum weight edge of crossing the cut. Okay? Is the statement clear? Every minimum spanning tree has to include a minimum weight edge crossing this cut. Okay? Let's just let me draw an example. Okay. Can somebody give an example of a cut in this graph? Okay, one side ADF, another side B. Another example? ABD. How many different cuts are there? In this example, how many different cuts are there? Can we count how many cuts are there in this example? Anybody wants to guess? 8 cuts. Okay, how's that? Okay, I have a question. Is this a cut? Is this a cut? I took A, C, F on one side, B, D, and E on the side. Is that a cut? Yes. Just because I've drawn it in a certain way doesn't mean a cut has to look physically with one on one side and the other on the other side. That's just a visual way for us to think about it. A cut is any set of vertices on one side and any set of vertices and the other set of vertices, the remaining set. The only requirement is both sets be non-empty. Okay, you can't say the cut is the entire set of vertices. Okay? Now, how many different cuts are there? N factorial ones is not quite true.
41.
Pardon?
41.
In this case, you're saying it's 41? No. How many different cuts are there? In this case or in general?
2 raised to n.
2 raised to n. How many different subsets of vertices can you form? The number of different subsets is, just think about it. In S, okay, so it's not exactly 2 raised to n, we'll just confirm that. So for S, every vertex can either be in S or not in S, correct? So for every vertex there are 2 choices. Either it can be in S or not. So how many ways can you select S? 2 to the n. Except for the fact that you're double counting. If S is on one side and S complement on the other side, that's basically the same thing as S and S complement. So it's 2 to the n minus 1. But then you want to remove the case where empty set is on one side. So the number of different cuts is 2 raised to n minus 1. Okay? So we will never be arguing statements about, oh, I'm going to write all the possible cuts, I'm going to look at every cut. Those things we cannot do because just the sheer number is exponential. Okay? But we will make statements like this, that let S complement be any cut. G. And it's important to keep in mind that when we draw a picture of a cut, it's just pictorial. It doesn't describe that, oh, all the vertices somehow. There is a possibility of making mistakes if you view the cut always as something being sort of have a nice visual representation. Okay, so that's something that we careful about. But in general, you will often be writing cuts like this. This is S. This is S complement. Okay, but it could very well be the case that I would draw A, C, and F here, and B, D, and E here. Okay. Yes.
What is A in the weight edge?
I'll clarify that in a moment. Okay. So there are a few terms here. So one is edge crossing cut. So this is the cut. When I say edge crossing cut, means any edge with one vertex on S and the other vertex in S complement. Okay? So if I were to take A, C, and F here, what are the edges crossing the cut? AB, AD, and there is no AE. Is there a CD? Yeah. Is there a CD? Yeah. And EF? Oh, sorry, EF, not BF. But DF and EF, and there is a CE also, right? Okay, so there are a bunch of edges crossing, right? Notice that there are edges on each side as well, and I have not drawn them, but these are the edges that are crossing the cut. All right? Good. So now these edges could have different weights. So we have different weights here. A to B is 5, C to B is 15, and so on. I'm not drawing all of them. So you have weights and weights. Minimum weight edge means an edge that has minimum weight among all the edges here. And a minimum weight edge means I'm acknowledging the fact that there may be multiple minimum weight edges, and we want to just make sure that T contains one of them. Okay? We don't know which one, but T has to contain one of them. That's the claim of this. That's the claim of the cut property. We haven't proved it. That's the claim. Okay? We sort of proved it last time, but I'll just repeat it. Any questions about the cut property? Yes.
So you say there could be like many minimum weight edges.
Yes.
Does there have to be some sort of threshold though, where you consider something a minimum weight edge versus not?
No. So the minimum weight edge means, what is minimum weight? So it could be confusing as to what I mean by minimum weight edge. What I mean is, you look at all the edges crossing the cut, pick the one that has the least weight among these. That's what I mean. I'm not referring to that edge has to have minimum weight among every edge or anything like that. So when I mean my minimum weight edge crossing the cut, I mean pick the least weight edge crossing the cut. And if there are multiple ones, it should include one of them. Okay? Alright. Okay, so now let's prove this statement. Okay, the proofs, the minimum spanning tree proofs are all proofs involving cuts and cycles and exchanging edges. So they just use sort of a handful of ideas, but it's very important to use them in the correct way. Okay, so let me draw this S as complement, and there are a bunch of edges crossing the cut. Okay, and bunch of edges crossing the cut, and T is a minimum spanning tree. What does T look like? Well, remember, T has to connect every vertex, right? T has to make sure that it connects every single vertex in the graph. Let's say there are 5 vertices on this side, 5 vertices on this side. So T might be connecting this with this, maybe this with this with this. There might be some things here, so I'm drawing more edge vertices here. This, and maybe T crosses here, this here, T crosses here, T crosses there. Okay, I've just drawn some. So the squiggly edges correspond to the tree. Okay, so T is supposed to be a minimum spanning tree. First thing to observe, 2 things to observe. T has to have an edge crossing the cut. You agree? Okay, and again, it's intuitively and pictorially obvious. How would you prove that T has to have an edge crossing the cut? Well, if T has no edge crossing the cut, okay, we will basically ask, we know that T is supposed to have a path between one word, T is supposed to have a path between any pair of vertices, right? T connects everybody. So T is supposed to have a path between any pair of vertices. So it's supposed to have a path between this vertex and this vertex. Okay? But let's say T does not include any edge here. Okay. How will it have a path between this vertex and this vertex? Well, suppose it's supposed to have a path, so let's follow that path. And in fact, T has a unique path. You agree? The tree only has one path between 2 vertices, so it has a unique path. So let's follow that path. It starts from here, and we'll keep following the path, and until the first time it crosses to the other side, and it has to cross to the other side because you have to eventually reach here. So you keep following it. At some point it's going to cross to the other side, but then at that time it's using an edge going from S to S complement. Okay. This is an obvious statement. We are not going to be proving this in our exams or problem sets again and again. But still, you should know if somebody asks you to prove it, this is how you could go about it. Okay, so some statements. So T has an edge crossing the cut. One common misconception is that maybe T should have only one edge crossing the cut. That's not necessary. T can have many edges crossing the cut. Okay. So in this example, T has an edge crossing the cut, and T has another edge crossing the cut. Okay? Alright. So this is T. What do we want to prove? We want to prove that one of the edges that T has crossing the cut has least weight among all edges in the cut. That's what we're trying to prove. Okay? So how do we prove about something like this? Standard, we'll try to prove it by contradiction. Okay? Suppose not the case. That is, the minimum weight edge let's pick any minimum weight edge crossing the cut, let's call it E. Let's call this E. Has weight less than all edges of T that are crossing the cut. Okay? Let's say the minimum weight edge crossing the cut happens to be this one. Okay, this is the edge. And then, as I said, there could be many minimum weight edge crossing the cut. Let me pick any one. Okay. So, every time we encounter it, we're going to, just like a greedy algorithm example, but many times the idea is we try to prove that the reason, so we're going to derive a contradiction, we're going to prove that this is not a minimum spanning tree because we're going to add E to the tree and then remove something and improve the cost of the tree, and that will be a contradiction. Okay. Okay. So what we want to do is add E. So what will happen if I add E to T? So again, remember T is some tree, no cycles in T. Every two vertices in T have a unique path between them. If I go ahead and add this edge U E, let's call this edge to be U V. If I go ahead and add to T, what will happen? It will form a cycle. Okay? Can you precisely identify the cycle it will form? What is the precise cycle that it will form? Yeah?
The path from the one end of P to the other edge of P and then E itself.
Exactly. There is a unique path from U to V. There is exactly one path from U to V in T. Of course, there are lots of paths from U to V in the graph. But there is exactly one path from U to V in T. And what is that path? In this picture, assuming I've drawn it correctly, this path is this, 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 this. Okay? Right? What do you observe about this path with respect to the cut? This particular path. It has an edge crossing the cut. Okay? So, it has an edge crossing the cut. So, and it has to have an edge crossing the cut. Again, for the same reason, this is the path going from this side to that side. It has to have an edge crossing the cut. If a path is going from this side to that side, how many edges can it have crossing the cut? It can have one. What are the other possibilities? not minus 1. The number of edges crossing the cut can have one edge. Can it have two edges crossing the cut?
After adding D, after adding D.
No, not counting. So path from U to B.
No,
It can never have two edges crossing the cut. People see why?
because.
You're going from one side to the other. If you go an even number of times, then you have to come back. So it will always have an odd number. Okay, but one is certainly a possibility, right? When it has to have at least one. Okay? So for us, it doesn't matter that it might go back and forth. But in this example, it's only having one, but it could have many edges crossing the cut, but it will have definitely at least one. So let me pick this edge and call it E prime. Okay? So add E to T, form the cycle. Let's call that cycle C. We know that C contains edge E prime. That crosses the cut. Okay? What do we know about the weight of P as compared to the weight of E prime?
Less than.
It's strictly less than. So what would you like to do? We would like to simply remove E prime. Okay? Now here is the question. Is the graph still, is the tree still connected?
Yes.
So we have taken T, union E, remove E prime. Is that still connected? Well, what do we have to prove to argue that it's connected? Again, it's sort of intuitive and obvious. But the main thing we have to argue is we have removed this edge, right? That means the main danger we have done is these two vertices which were previously connected are no longer connected. Okay? As long as you can make sure that they are still connected, we are done. Because any path that could possibly want to use this edge can take the alternative path around, right? The B2. So, well, it's easy, right? I mean, if you remove this edge, how are these two connected? Well, this was a cycle, so there was another path going through it. So they have a path. Okay? So, T union E minus E prime, it is connected. How many edges does it have? Exactly the same as T, n minus 1. So it's a tree. So it's a spanning tree. What about the weight of this tree? It's strictly less than the weight of T. But that's a contradiction because T was supposed to be a minimum span. Okay? So T union E minus E prime. This is a spanning tree of lower weight, which is a contradiction. Okay? Any questions? Yes?
So are we assuming that this is a weighted underactive graph?
Yes, the problem, I didn't say that. Thank you. No, I said it. Weighted. All the edges have weights.
Right, so I guess where I'm a little bit lost is what if the weight for E just happened to be really, really high, higher than all the other?
No, E is the edge of minimum weight in the cut.
Okay,
That's the definition of E.
okay.
Okay? That is minimum weight edge E. Okay, so what are we trying to argue? We are trying to argue that the minimum spanning tree is supposed to have the minimum weight edge crossing the cut. let's suppose it does not have. So let's pick the minimum weight edge crossing the cut, E. There might be multiple choices for E, so just pick any one of them that is, that's our E. So this argument absolutely crucially uses that E is or the minimum weight edge crossing the cut. It might have much higher weight than edges here, possibly, but on the cut, it has the least weight. Yes?
So what is the guarantee that choosing a minimum weight will span the entire?
No, just by itself it won't span. We have taken the tree T, we have said if E was not included, then, and E prime, all these were bigger than E, then if I add that and remove this, I improve my solution. So what was given to me is not a minimum spanning tree. Any other questions? Okay, so we're going to do one more similar property, and that's the cycle property. So the cut property tells you what your minimum spanning tree should have. The cycle property tells you what your minimum spanning tree should not have. Okay? Cycle G. Let C be any cycle in G. Just let me just write that. C be any cycle in G. And let E be a max weight edge of C. Okay, again, what I mean by a max weight of edge of C, look at all the edges of C, E has the maximum weight. There could be multiple choices, but I'm picking one of the maximum. Then there exists an MST that does not include E. Yes? You have a question?
Question about the edges crossing a cut.
Yeah.
There can exist multiple edges crossing the cut, but it will include the minimum edge, right?
Correct. So there are lots of edges crossing the cut. A minimum spanning tree could include many of them, but it has to, one of them has to be a minimum weight edge crossing the cut. Okay? So let C be any cycle in G, let E be a max weight edge of C, then there exists a minimum spanning tree that does not include this edge. Okay? Okay, so let's try to prove this. As always, our proof will be sort of by contradiction. So we will take an MST and we will make a change to it, make it so that it doesn't satisfies. So suppose let T be any MST. Okay. And let C be a cycle. C is the given cycle. If T does not include E, then we are done. Great. We want to prove that there exists a minimum spanning tree that does not include E. Again, what is E? E is the maximum weight edge of some cycle. Okay. Okay. So in this cycle, which is E, the edge of weight 15, and if there are multiple choices, then you pick one of them. So this is E. This is U, this is P. Okay, let's call that UE. So let's suppose let's suppose we are given a tree, and if the minimum spanning, we are given a minimum spanning tree T, and we are told that it does not include E, then we are done. But now we are given a minimum spanning tree. In the other case, it actually does include E. Maybe it includes some other edges here. Maybe something else going on here. Drawn some. So all the squiggly edges again are the minimum spanning tree edges. So of course it cannot include all the edges of the cycle. Do we see that? Because then it will have a cycle, and minimum spanning tree has no cycles. So that's not. But it could include some of them. It certainly includes this particular one, right? But it could include some of them, and then okay. So, is this a spanning tree? Is everybody connected? Yeah. Okay. Okay. So what do we do in this case? So in this case, we want to be able to demonstrate that we can remove E from T and get maybe a better minimum spanning tree, and that will be a contradiction. Okay. Okay. So what will happen if we remove E from T? What will happen if we remove an edge from the tree? But it will disconnect it. Notice it won't disconnect the graph, but it will disconnect the tree. Okay? So U and V, and this was the edge, and let's say we removed it from the tree. Then it will, how many parts will it split the tree into? Exactly 2 parts. One part that includes everything that U will be connected to. And by the way, when we say connected, we don't mean edges, right? We mean paths. So anything that you can reach, and anything we can reach. Okay? So in some sense, it forms a cut. I mean, it sort of gives notion of a cut. Okay? So this these are other edges. Spanning tree. This side, the other edges of the spanning tree. Okay. Notice that in the graph, there are many, many more edges. This picture I'm drawing is just for the tree. Okay, so, but it splits the tree into 2 parts. And this was the edge E that we don't want the minimum spanning tree to have. Okay? But I've removed it. Now what do I need to do? I need to connect them. Right? This is the cut. Okay? I should be careful in my statement. No, that's fine. No, that's correct. Okay, so this is the cut, and we know that this edge is a maximum weight edge of a cycle. Good. Okay. So what do? I remove this edge E. If I remove this edge E, what do I need to do? I need to add another edge. What are the possible choices of edges that I should be adding?
Minimum spanning one.
Well, Will it help me if I add an edge here? No. In fact, what will happen? That will create? Will it help me if I add an edge here? No. So the only edges I should consider are the ones crossing this cut in G. Okay? But what if I tell you there is no edge, other edge? There has to be, because we are talking about edge E being a cycle. So if edge E is part of a cycle in G, then let's look at that cycle. Okay, that cycle might consist of something here, something here. Remember, that cycle has to cross this. Just like a path from here to here crosses the cut an odd number of times, a cycle crosses the cut an even number of times. It has to come this side, this side. So if there is one edge, there better be another edge. There could be many edges, but there is at least one more edge. So let's follow that. So it is some cycle. So it goes like this, maybe like this, this, this. Let's say this was the cycle. Yes, that has some colored chalk. Anyway, so this is the cycle. But it crosses the edge at least once more. Okay? So we are removing this edge, and what we will do is replace it with this one. Let's call this edge E prime. What do we know about the weight of E versus weight of E prime? E is the maximum weight edge. So E prime is no bigger than E. Okay, so weight of E prime is most. Okay? And just by the same logic as we did before, if I remove E, put in E prime, the tree is now connected. Why is that? Everything here was connected before. Everything here was connected before. The only thing that was not connected was here to here. If I add this edge, it will be. So if I add E prime, subtract E, add E prime. By the way, we will sometimes use this notation. It's mathematically sort of not precise, but all it's saying is I take the tree, remove E, add E prime. Okay? Let's call this tree T prime. What about the weight of T prime? The weight of T prime is weight of T minus the weight of E plus the weight of T prime, which is strictly less than weight of T. So if T is a minimum spanning tree, then so is T prime, or there is a contradiction. Right? So if T is a minimum spanning tree, then T prime will be also minimum spanning tree, because T prime has weight less than equal to weight of T. So T prime is a minimum spanning tree. So we have shown that there exists a minimum spanning tree that does not include E. Yes?
Do we disregard like the property that a tree has no cycles? When you say MST, but there's actually a cycle on one of the cuts.
No?
Disregard that?
No, we did not have a cycle. Where is the cycle? The cycle came about. The cycle C was in the graph. Okay? So this drawing, this picture, this is a cycle in the graph. It only includes these edges. This is the minimum spanning tree edge. This is the minimum spanning tree edge. This is the minimum. This is not in the minimum spanning tree.
Oh, okay. I see. So the one on the right.
This is not in the minimum spanning tree either. So that cycle is in the graph, and it includes some edges from the minimum spanning tree. It does not include some other edges. Okay. And what we are doing is, from that cycle, we are finding an edge E prime that is crossing the cut, and we are removing E and adding E prime. Okay, and there are no cycles formed because this edge is not there, and these edges are also not there. There was a question at the back. No? Any other? Yes.
So here are they saying that any MST, so basically from a cycle, the max weight edge,
Yeah.
there can be a valid MST that has the max weight edge.
That is possible if there are multiple max. I think it's possible if there are multiple max weight edges, that there is an MST that includes that.
If there are multiple max
Max weight edges, yes.
But if there are not, then no MST will include that max weight.
If all the edges were, let's say, unique weight, and E was a max weight edge of a cycle, then no MST should include it. Because we will get a contradiction. Because if all edges were unique weight, then weight of E prime will actually be strictly less than weight of E. Then this would lead to a contradiction. Okay? Any other questions? Okay, so these are the two properties, and both of these properties lend themselves to very nice greedy algorithms. In fact, there is sort of a slew of greedy algorithms we can develop based on this. The idea being that if ever I find a minimum weight edge crossing a cut, if I find that I have a spanning tree, I'm building my spanning tree and there is a cut that I'm not crossing, then I can go ahead and add a minimum weight edge crossing the cut. Because that's what the first cut property says. This says that if I ever find I can go in the reverse direction, I can start from every edge in the graph, and then I can check to see, oh, is this edge a maximum weight edge of a cycle? I can go ahead and remove it. And I keep doing that, then I can find the spanning tree. So you can build a spanning tree using both techniques. Okay? We will look at two algorithms that both use sort of repeatedly this technique, but you can also imagine algorithms that repeatedly use this technique or some combination of those two techniques. Okay? Okay. So let's do the Driscoll's algorithm. So, the idea behind Driscoll's algorithm is the following. Let me draw a graph. Okay, let me put some B, C, there are 9 vertices in this graph, and let me put some weights. I'll put distinct weights. Everything. Okay, so the idea behind Driscoll's algorithm is that we will start from an empty plate and we will build our tree. Okay, so you have A, B, C, D, E, F, G, H, I. Okay? And since we are focused on finding, we are going to use the cut property, and the cut property repeatedly looks at minimum weight edges crossing the cut. What we will do is, we will look at all the edges in sorted order from minimum weight onwards. And if you ever find an edge that is crossing a cut that has not been used before, we'll go ahead and include it. Okay? Okay. So let's start from that. So we'll sort all the edges. So we look at the first edge. What's the minimum weight edge? The whole graph? AB. Okay. What cut does it cross? Well, it crosses many cuts, right? It crosses the cut A separated from everybody else. It crosses the cut AG separated from everybody else. It crosses the cut AEC separated from anybody else, and so on. But it is the minimum weight edge in the graph, so it's going to be the minimum weight edge of all of those cuts. Ready? By the cut property, the minimum spanning tree there is a minimum spanning tree that includes that minimum weight edge. Okay, pass. So I can go ahead and include that edge of minimum weight because it's crossing the cut. Let's say it is crossing the cut A separated from everybody else. Okay? The cut probability tells us that there is a minimum spanning tree that has to include this edge. Okay? So now I'm done with 1. So what is the next weight, minimum weight edge? 2, AE. So now notice that the cuts that I will consider, in every cut that I will consider, AB will be on the same side. Because AB have been connected together, you can never find an edge, a minimum weight edge crossing a cut that separates A from B. Because we've already included the minimum weight edge crossing the cut separating A and B. Okay? So A and B will be always treated as one side. Okay? So the edge 2, minimum of weight 2 connects, let's say, the cut with A and B on one side, everybody else on the other side. You agree? And it is the minimum weightage of that cut. So we can include that. Now that we have done this, A, B, and E will be always together in everything else. We will never add an edge inside A, B, and E. Why will we never add an edge inside A, B, and E? Because it will create a cycle. Okay? So that's all we're going to do. We're going to put the next edge. We're going to see, is it forming a cycle? If it's not forming a cycle, we'll go ahead and include it. Really, very simple. What's the next edge? Edge number 3, AG. If I add this, is it forming a cycle? No. Why is that? Because it is an edge crossing this cut. A, B, and E on one side, everything else on the other side. Okay, that's 3. What's the next one? PH. That's also fine. What's the next one? GE. Can I add that? No. So GE will not be added. What's the next one? 6 is FI. So notice that I started off building this tree here, but now I have left us and doing something else. So, but we will always have a forest. Okay, a forest is a collection of trees that have basically a collection of trees, so no cycles anywhere. But now remember, F and I will always be part of one component. You will never try to add more edges to inside this. Okay, that's 6. Then CD, 7. Then CF, 8. And then DC, 9. And we'll be done.
So essentially we go until we add every single node.
We have to cover every single node. Every node was there from the very beginning. We keep on adding edges until everything becomes connected. And we keep on, so we are looking at edges in increasing order of their, and we keep adding edges as long as they do not form a cycle. Okay, so that's the algorithm. sort edges in increasing order or non-decreasing order of their weight. For E in this order, go through these edges in that order. Okay, I should say that initially the tree is empty. If T union E does not have a cycle, if E does not form a cycle with T, then you change, you add E. That is the algorithm. Okay. There are some things that are sort of, we know this is easy. Sorting edges, we know how to do that, very easy. Going through these edges in this order, we know how to do that. This, we know how to do it, how to form a cycle, find a cycle. We have looked at a lot of problems like that. And you can just do a depth first search from one endpoint of U and see whether that reaches the other endpoint in T. If it does, then you don't include it. If it does not, then you go ahead and include it. But we will see that there are much better ways of doing it. For now, I'm going to leave it like this, and I'm not going to analyze the running time because we're going to look at a better way of doing this, better way of implementing this. Okay? Any questions about this algorithm? All right. So let's look at a different algorithm. This algorithm is sort of looking at all the vertices, and then it's forming sort of clouds around them. Yes.
So essentially, for this algorithm with Crystal, the running time is going to be impacted by whatever we do with number 3.
Correct. Yes. It's going to be impacted by whatever we do. Yes.
Is there a reason why we're not using the cycle property? Because, I don't know, to me it seems more obvious, detect a cycle, pick the largest edge, knock it out, find another cycle, pick the largest edge, knock it out. Do this until you don't have any more cycles in your graph.
Correct. So let's go with that. So we could easily do that. So let's try to see what kind of, let's try to actually develop an algorithm ourselves. Okay. So let's say we want to go in the reverse direction. Okay. So what will you do? What's the algorithm? So you're going to use this, let's call it anti-Kruskal. So we start T equals empty. We actually no, T is not empty. What is T? T is the entire set of edges. Then we sort edges in the decreasing order of their weight. What do you do with the first edge that you pick?
If it is part of a cycle, remove it.
If it is part of a cycle, remove the edge. Okay, let's write that. Write it down and let's even run it on this graph and see what happens. So T equals empty. Second is, sorry, T is all the edges. Sort E in decreasing order of weight. if for E in this order, if, what was the condition? That if E forms a cycle. So if there is a cycle containing E in T, then what do we do? If there is a cycle containing E in T, what do we do? We remove it from T. So T becomes T minus E. Okay, or T minus. Perfectly gradual. Okay? Let's just run it on our example graph. So, I guess it would have been easier with the graph. C. I. And then BC.
G, E, and G.
G, E, and
B, E.
so 1, 2, 3, 4, 5. Okay, all right. So we are going in the reverse direction, reverse thing. So it's
What's the cost of BE?
B is, oh, so I don't know.
Never assigned anything.
I never assigned it. All right. Let's make it the largest one. So BE should be, let's make it 13, 14, 15. Notice that if we make it lower than anything else, it will change, right? Okay. So, so what do? We start with 15. Does this form a cycle? So we just remove it. When we look at 14, does it form a cycle? Yes. 17, does it form a cycle? Yes. 12, does it form a cycle? Yes. 11 forms a cycle? Yes. 10 form a cycle? Yes. Does 9 form a cycle? No. See that? Because if you, one way to check whether it forms a cycle is if you remove it, does it form a cut? Another way to check is exactly how we have done many problems like this. Does it form a cycle? If you check whether there's another path from B to C that does not. So we will leave 9 alone. Does 8 form a cycle? 7? 6? No. 5? Yes. 4 no, 3 no, 2 no. Okay? This is also a fine algorithm, and there may also be a smarter implementation of this. Let's try to review the running time, just so that if we just did it the way we were thinking of doing it. So we sort all the edges along with the state. If let's say n is the number of edges, m log n. Okay, but notice that m, what is the maximum that m can take?
N
No? N choose 2, so something like n squared, and log of n squared is 2 log n. So you will often, and see we are ignoring the leading constants, so you'll often see, sometimes you might see this, and sometimes you might see m log n. And within the theta notation, they are both the same. Okay, so don't get confused by that. We often use this instead of this. Okay, so that's m log n or m log n. Then we go through every edge and we check whether there is a cycle. How long will this take?
Linear every time.
It will take linear, and it could take linear in the, depending upon how you do it, you could probably do it in time, but certainly it will take linear time. So, and we are doing it for every edge. So this will take at least m times n time, maybe even m squared time. Okay. We are going to look at the implementation of Kruskal. That takes, where this is the time taken for sorting is the main dominant time. So we're going to give a theta log n algorithm for that. Implementation for that. Okay? Any questions about this? Okay. So let's go over the other algorithm that also uses cut property, which is Prim's algorithm. So what Prim's algorithm does is it starts from one vertex and builds a tree around it. Okay? And it keeps building it as long as everything is not yet connected. Once everything is connected, it stops. How did Kruskal work? Kruskal had different components building in different ways, and then until everything connected together. Here you're just starting from one place in the. So the way you do this is you have your set, initial set, let's call it, let's say you're going to start from the vertex S. Okay. This is one vertex in your graph from which you're going to start building your tree. So what you do is you, for every other vertex, you will keep track of essentially the edge crossing the cut that we will be looking at. So every time we will have a notion of a cut, and we will have we will keep track for all those vertices that have edges crossing that particular cut. We will keep track of the least weight edge, because we are going to find we want to pick the least weight edge crossing the cut. So initially, if S is on one side and everybody else is on the other side, this is the vertex, little s on this side, everybody else is on the other side. The only edges crossing the cut are the edges that from S. Okay? So for every other vertex, for every other vertex, we assign, let's say, we use the C, cost for the edge, for the vertex. We assign CV to be the weight of the edge going from S to V. If there is no edge from S to V, then the weight will be set to infinity. Infinity. Okay, you want it basically indicate that there is no edge. Okay, so let me write it. CV is weight SV if SV is an edge. Otherwise, okay? Clear? Now what do? We are here. What edge do we want to pick from here? Minimum weight edge, right? So, while S is not the entire set of vertices, so you keep adding stuff as long as you have not yet connected everybody. So while S is not the entire set of vertices, find V that has minimum CV look at all the vertices on the other side of the cut and pick the one that has the lowest C value. Okay? Move that over. So we're going to add V2. Let me actually make another note here. When you set CV to be equal to the weight of the edge from S to B, you also set up, you keep a track of this notion of a parent, how you're connecting V. You set pi of V, which is the parent of V, to be S. Okay? So find V that has minimum CV in this, add V to S, and then add the edge between pi V and V to T. Okay, so we have added the edge from pi V to T. Okay, so there is one more step that needs to be done. I will put that in a moment. But let's try to, before we do that, let's try to understand what is going on with this example. Okay, so we are going to keep track of the set S, and we are going to have this cost table. So cost and phi, C and phi. Okay. So what source should we start from? We can start from any source, any particular, let's say H. So F is H. Okay? So all the others will have us A, B, C, D, E, F, G, I. Okay? So we will start with S. For every vertex, every other vertex, we will assign a cost and a parent. So for, let's say, let's go through every single vertex. A. Okay? Does A have an edge to H? No. So A will have a cost of infinity. And if you have a cost of infinity, you don't need to define the parent. B. Does B have an edge to H? Yes. 4. And parent for BH. C. Does C have an edge? No. D doesn't have an edge. E, no. F, no. G, yes. I, okay. Ah, sorry. Okay, good. So now what are we doing? Now we have set all this up. This is the initial setup. Now we are building our tree. Okay, I should say that initially the tree is empty. Okay, so from H we pick. So now we look at the vertex in this table that has the minimum value of C, which is B. Okay, so we will go ahead and include that vertex, move it to S, and add this edge from that vertex to its parent to our tree. So this edge gets added to the tree. Okay, so I'm going to remove this from B. But now that that has been added, the cut now we are looking at is the cut that separates B and H from everybody else. We have already looked at the edges out of H, but we have not looked at the edges out of B. So we will examine all the edges out of B and update the costs for the other vertices if it applies. Okay? So let's go over that process here, and then we will write the piece of code for that. So we'll go, the vertex that we have added is B. So I'm going to look at all the edges out of B. So just go through all the edges. So B to A. This weight is 1. Is it better than A's previous weight? Yes. So I'm going to update that to 1 and update that to B. Okay? Then B to E. That E was 15, right? Or 15, yes. So B to E. Is it better than infinity? Yes. And this will change to B to C. 9. B to, is there anything else? That's it. And B to H, we don't need to do anything about this. Okay? So that's our new table. Okay? So let's keep on going. Now we will pick the minimum number from this. Which is the minimum number? A. So we're going to include the edge A, B to A, and then now we will examine all the edges out of A. The edges out of A are A to E, which beats 15, so it's 3. Now A to, sorry, not 3, 2. A to G, 2, A. Sorry, 3 and A. And that's it. Now we will look at all these and we'll pick the minimum, which is, by the way, A should be removed. Okay, this is not a particularly visually clear table, but you understand what's going on. The next one we will pick is E. So let's just follow this on this picture. So next we will pick E. And then we will go through all of these edges and update. Will anything get updated? G will not get updated. Why is that? Because G's previous thing was 3. So 5 is not less than 3. G will not get updated. B is already there, it doesn't need to get updated. Will F get updated? Yes. That F has an infinity, so that will get updated. And so on. Okay? So everybody gets the idea of how the algorithm is proceeding. The next edge that will be picked will be
A to G.
yeah, E to G. Sorry, A to G. Then you will pick B to C. Then we will pick C to D. Then we will pick C to F. Okay, so I have to finish this off, so let's write what we are doing. We are going through all the edges out of the vertex that we are, so 8. We are going through all the edges for out of the vertex V, for Vx in E. Okay, so one of the endpoints has to be V, the other endpoint is X. And what do? We update, we check whether the cost for X, if the cost for X exceeds the weight of the edge Vx, what do? We replace the cost of X with the weight of the edge Vx, and we update the pi to V. Then cost of X becomes the weight of Vx, and pi of X becomes so that's the output. Yes?
Which is quicker for our,
Good question. We will see that the Prim's algorithm can also be implemented in theta and log n time. Okay? So there is no difference. Amazingly, even though this problem has been studied for 100 years, we still do not know that this is the best we can do. Okay, it's a beautiful open problem. There is some work, there are some really complicated ways of reducing this a little bit, but in the theta notation. So from a practical standpoint, both of these algorithms work very well. It turns out that if you're looking for some kind of a distributed procedure where you're trying to build your spanning tree from different places, Kruskal's algorithm is a better way of thinking about it. Otherwise, it doesn't matter. Okay. Okay. Are the algorithms clear? Okay. We are not proving their correctness because the fact that they find the minimum spanning tree is because they are all both relying on directly on the cut property. The cut property tells us if I give you an edge in a minimum cut, there's the minimum weight in a cut that your tree is not crossing right now. Go ahead and include it, and that's what both of these algorithms do. They pick different cuts. This Prim's algorithm sort of grows the tree from one side and then keeps on picking edges from those cuts. Kruskal's algorithm is all over the place and picking edges from that. Okay? In the same way, we don't have to prove that anti-Kruskal algorithm is correct because it just follows the cycle property. That it repeatedly removes those edges that are part of a maximum weight, are a maximum weight edge of the cycle. Okay, so let's try to look at the data structures we need for both of these algorithms that will yield the stack. Okay. So let's do that one first. Actually, no. Let's do Prim's first, and then we'll do. Okay. So, what does Prim's algorithm? What data structure do we need? We are trying to maintain this table. Okay. This table has two entries. One is a cost, and the other is a pi. Pi, let's not worry about it. The pi changes when the cost changes, then you change the pi. Right? So that's one. So the main thing is how are we maintaining this pi, this cost. So let's look at the cost table. What operations are we doing with the cost table? Initially, we are inserting some vertices, okay, with a certain value. So we are inserting V with a certain cost. That could be an operation. We're inserting an entry. Then what are we doing? Finding a V that has the minimum cost. Okay. We are doing a find min. And what are we doing with that V? Once we find it, we are actually removing it from V minus S. Remember, we are removing it from the table. So we are not only finding the min, we are actually deleting it. If you find the min, we do something with it, and then we remove it. Okay? What else do we do? Basically that's it, right? Oh no. And then we update it. Okay? Then we update the key. Okay? So we are doing insertion, we are doing find min, really we are doing extract min, because we find it and then we remove it. So we are inserting, extracting min, and then updating the key. How many times do we insert? We insert every vertex, that's not in this, not the original vertex. So n minus 1 times, or basically n times. So we do this n times. N minus 1, if you have to be precise. How many times do we extract min? We are repeatedly adding removing a vertex until every vertex has been removed. So that's n minus 1 times. How many times do we update the key? When do we update the key? When we find an edge that gives me a better value for something. Okay? But how many times is this going to go into this loop? So let's look at the loop here. How many times is the while loop going to execute? N minus 1 times. So that's the number of while loops, n minus 1. How many times is this going to go? For every edge adjacent to V. How many times is that loop? As many edges as V has, the degree of V, which could be as much as n minus 1 or something like that. So then the number of times you will go in here, if you one crude bound would be n times n squared. Except that when you think about it, the number of times you will go inside is only as many, maximum the number of times you will go inside this loop is the total number of edges in the graph. Okay? So the number of times you're going to, and this is the only place where we have the update key, right? So the number of times you're going to do the update key is no more than. Okay? So you want to find a data structure that does these things well. Okay? And there are a number of data structures you can use. So can anybody suggest?
Priority queue.
So heap, also a balanced binary search tree. All of these data structures would work. What does a heap do? Okay. It does extract min in log n time. It finds min in constant time. It immediately finds the min because you keep the min at the top of the heap. But then you have to remove it, then you have to do some heap adjustment. That you can do it in log n time. Update key is like identifying the location and then removing it and updating it and adding it. That's like insert plus delete. That's again can be done in log n time. And insert also can be done in log n time. Okay. So the whole thing can be done in m log n time, theta m log n time. And by the way, exactly the same thing holds for balanced binary trees. Search trees. Okay? Okay, so that completes Prim's algorithm. We will go over Driscoll's algorithm's data structure next time. Okay? Alright. So, if you have not collected your midterm or your first quiz, your second quiz is still being graded. So if you have not collected your midterm or your first quiz, please come by and